So our next speaker is Antônio Duarte Pereira from UF, which is a university in Rio de Janeiro. And it's a pleasure to have him. He's going to talk about some cool stuff involving the asymptotic safety program in quantum gravity. So please, Antonio, whenever you're ready.
Yeah,
Right.
so
Thanks.
thank you very much. Thank you very much to the organizers for the invitation. And thank you very much for the audience, for being here the last day after lunch break and so on. So it's really nice of you. Okay, so in this conference, I have to say that when I was invited to give the talk, I was super afraid of talking about, things that we can measure in a lab from quantum gravity. And then I started thinking a little bit about what to talk, and instead of talking about I could choose some particular works of mine, I decided to give some sort of overview, but not to be confused with a review talk about what is going on in this field of research, which is known as asymptotic safety. So John already used these words in his talk. I think in the first day of the conference, Philip Stamp also mentioned asymptotic safety. So I'll try to explain a little bit what asymptotic safety is and explain some possible or some potential phenomenological consequences. Okay, before I move on, I have the obligation to make this propaganda. So there is now the International Society for Quantum Gravity that some of you I know that are members of, but if you are not and you would like to join, you can access this website, and there is a form that you can write down and become a member. And there is also a YouTube channel full of interviews with quantum gravity researchers, and also full of lectures, including, for instance, John's lectures on effective field theory for quantum gravity. So you are very welcome to join, and I hope you do so. And also let me say that along this week we saw many tabletop experiments in order to test quantum effects of gravity, but in this talk I'll be talking about what I come from a QCD community, so what I see as a lab is things like this, okay? So I'm not going to talk about tabletop experiments and try to develop very tiny masses and things. So it's not my field of research. I don't have anything to add on that. So I'll talk about things that we could potentially see at the LHC. Okay, so let me start, since, as I said, I'll be talking about things that are quite, slightly different from what we have heard so far. Let me try to state some common ground so that we start from the same point. Well, we know what we actually know about the fundamental interactions in our universe is that there are 4, and 3 of them are described by the standard model of particle physics, and 1, the gravitational one, is described by general relativity. And if you think about these frameworks as, 2 frameworks that work separately, they are remarkable theoretical frameworks, and they describe essentially everything that we see in those experiments and very sophisticated measurements that have been made over the past decades. However, as we know from general relativity that we have solutions, for instance, that describe a black hole, and we know that there is a singularity at r equals to 0 in the Schwarzschild solution. And, some people claim that this is GR predicting its own breakdown, and also some people claim that quantum gravity should be the theory that resolves the singularity. And we nowadays see black holes in the sky to some extent. We detect gravitational waves by the merging of black holes. We even take pictures of black hole shadows. So, if those objects or the way that we describe those objects by general relativity is fully complete, then we have to, or at least would like to say something about the singularity resolution. And there is also another singularity, which is the initial singularity, namely the Big Bang, that we also put some expectation that quantum gravity will tell us something about that. Okay, now let me talk a little bit about the standard model of particle physics. Well, it is a quantum field theory. And in quantum field theory, when you do a calculation, typically the result is infinite. So you have to renormalize, you have to remove those infinities. And the standard model of particle physics is a theory that is perturbatively renormalizable. And this was a guiding principle in order to construct the standard model. And if you are not familiar with that, there is another concept that is very important, which is the fact that the coupling constants, namely the constants, or the, let me say, the parameters that measure the strength between interactions, they run, right? They are not really constants. But being perturbatively renormalizable, we know that the standard model is a predictive theory because we have to fix just finitely many conditions in order to do calculations. And moreover, I think also John mentioned that, we also know that the standard model, besides being perturbatively renormalizable, it develops the so-called Landau poles in some of the couplings, namely the abelian hypercharge coupling and the Higgs-Yukawa sector. They are couplings that explode at finite energy scales, okay? So the standard model also has singularities in this sense. So you're seeing here that this is just a cartoon to show that there is a coupling that for some finite energy scale, this coupling just blows up. So the same criticism that we are used to listen to GR, we could also transfer to the standard model and say, well, the standard model also has singularities, and we want to cure that, okay? And my claim here, which might be seen as a provocative statement, is that the standard model is a perturbatively renormalizable quantum field theory, but we are seeing that perturbative renormalizability is neither necessary nor sufficient to ensure that a quantum field theory is valid across all energy scales. We are seeing that the standard model has a cutoff at finite energies. But still, we do computations with the standard model, we measure things, results are great, we have very precise predictions, so we are all happy about that. Okay, so we have these two patches of observed world, namely general relativity and the standard model, and they are very successful, and of course, I mean, they are not the complete story. We know for sure that there is new physics that we are missing, for instance, neutrino masses and the dark side of the universe, namely dark matter and dark energy perhaps. And both theories, they have some structural problems. That's, I'm saying here that is the existence of singularities. And well, there is this thing that we typically learn in GR courses, that energy and matter deforms the space-time, and space-time, well, tell how those things should move. Well, now we're talking about quantum fields that deform space-time. So, well, unlike Oppenheim in the morning, I think that space-time will also fluctuate quantum mechanically. But I mean, this is my prejudice, okay? This is a hypothesis. So there is a bold hope, which is now if we take into account quantum gravity and matter, can we, I mean, if this theory that takes into account both sides of our understanding of the universe, Can we resolve the singularities of GR and the standard model? So there is an immediate way of implementing this quantization of GR plus matter, which is to do a perturbative quantization of gravity plus the standard model degrees of freedom. And as we have heard from John, the resulting theory is perturbatively non-renormalizable. And, well, also John told us that, well, this is not exactly a problem because you can absorb all the infinities by adding more and more counter terms. The issue here is that you have to add infinitely many counter terms. And therefore, the theory, the final theory, let's say, is not predictive. You have to fix infinitely many couplings. But this means that although the theory is perturbatively non-renormalizable, this means that for sufficiently low energy scales, we can still make predictions. So in this sense, there is no incompatibility between the formalism of quantum field theory and general relativity, as is often said. I mean, you can do calculations and you can make predictions. If nature gives what you compute, it's a different story, but I mean, you can do the calculation. So the idea is simple. I mean, well, it's not simple. It's simple after someone did, but you introduce an ultraviolet cutoff, and typically we put at the Planck scale, and then you do computations below the Planck scale. We can, for instance, compute the quantum corrections to the Newtonian potential. Okay? So in this sense, I would say that we do have a theory of quantum gravity because, I mean, as the standard model, if you see the standard model as a theory that is valid up to some cutoff because of the Landau poles, well, this theory of quantum gravity is also a well-behaved theory up to this cutoff, okay? The only difference is that at some energy scale, you have to stop and do not trust the results anymore because your effective field theory expansion does not make sense anymore. So, well, you heard things in this direction from John, and you probably will hear things in this direction from Alessandro after the break. Okay. So just a comment about scales is that, well, typically we impose that quantum gravity effects take place at the Planck scale, which is a ridiculously short distance. It's 10 to the minus 35 meters. And just to compare, if you translate it into energy scale, this is 10 to the 19 GeV, and the electric scale is it's 100 GeV. So we are really, really far away from testing quantum gravity effects or direct quantum gravity effects that takes place at the Planck scale, namely 10 to the 19 GeV, with LHC experiments that are typically bounded at the scale of 1 TeV. Okay? However, so typically what we say is that the physics that happens at very, very high energies will be completely washed out when we go to very low energies compared to the Planck scale. And, I mean, we will not see any sign of quantum gravity in the lab or in the LHC. But let me make we just heard a lot about fluids. Let me just mention that, for instance, although a lot of information that happens at the microscopic level is washed out when you go to a macroscopic level, there are still some microscopic imprints, like, for instance, if you think about fluids, the viscosity of the fluid. So there is a microscopic imprint in macroscopic quantities as the viscosity that comes from this very microscopic structure. So we went to search for the analog of that in quantum gravity coupled to matter. So now we have to find a mathematical way to bridge those scales. And the mathematical microscope or the mathematical magnifying glass that we have in quantum field theory is the renormalization group. And the renormalization group was an idea that was, well, made in the way that I will use here by Wilson. And essentially, this is a technique that, well, it tells you how to encode the effective dynamics of a theory at a scale k with an effective action sk. Okay? So if you want to do physics at some given scale k, you don't need to know everything. You just need to know this sk. Thinking about this cartoon here, this means that I have to integrate out all the field modes from an ultraviolet cutoff, for instance, down to some scale k, and this will incorporate all the dynamics, the UV dynamics, in an effective theory that is valid at a scale k. Well, of course, if you start lowering k, you're going to take into account all the fluctuations, and, well, you're going to have a sequence of effective actions that will define a flow. Okay? And this is the renormalization group flow. So what I want to propose, or what the community has been proposing, is that we can use the renormalization group as a bridge from quantum gravity scales to particle physics scales. And we want to search for quantum gravity imprints in this game. Okay, so again, so this plot here is just a plot of the running of the coupling constants in the standard model. And you see that the running stops precisely at 10 to the 20, which is roughly the Planck scale. Because after that, well, it's a bit meaningless to just look at the standard model as standalone theory, because quantum gravity effects should be taken into account. So you see that up to the Planck scale, we don't have any Landau poles in the standard model, but at trans-Planckian scales, we do have, as I argued before. On the other hand, quantum gravity effects are relevant precisely from this scale analysis or this dimensional analysis that I mentioned. They start to get relevant precisely from the Planck scale on. And since the couplings of the standard model develop Landau poles at the after the Planck scale, there is, well, let's say a naive hope, which is that quantum gravity fluctuations that are relevant or strong after the Planck scale perhaps can cure the singularities of the standard model. And so there is an interplay after the Planck scale between gravity and matter that we should explore. But of course, we know that after the Planck scale, well, we don't have a theory of quantum gravity, so what should we do, right? So what I'm trying to look for is a fundamental quantum field theory, so it's not an effective field theory, that encodes gravity and matter. And if I manage to find such a theory, what are the consequences to particle physics? So there is a logical possibility, which is that the coupling constants of the full quantum field theory that involves quantum gravity and matter degrees of freedom, they reach a finite value or a fixed point. They reach a renormalization group fixed point, which means that at this fixed point they cease to run, and the theory becomes a scale invariant. Okay? So the idea behind asymptotic safety is precisely to, well, question whether such a fixed point exists. Okay? But let me just explain a little bit what this means. So in QCD, we know asymptotic freedom, namely, if you go to very large energy scales, the coupling will just vanish. So you have a fixed point, and the fixed point means that at the fixed point your theory is free. Okay? This means that perturbation theory is a very useful tool to probe such a fixed point because the interactions become smaller and smaller. So you have an expansion parameter that is trustable. But there is another, let me highlight that, as John said yesterday, quadratic gravity features such property of asymptotic freedom. So perturbation theory is a good one, is a good tool to probe the high energy behavior of such theory. But there is another possibility, which is that the coupling constant do not reach a Gaussian or trivial fixed point, but a non-trivial fixed point in the ultraviolet. And this G star, which is the value of the fixed point, can be significantly larger than 1. So perturbation theory is not trustable anymore, and you have to use some sort of non-perturbative technique in order to probe the existence of such fixed point. And this is what is called asymptotic safety instead of asymptotic freedom. So, phrasing again, could quantum gravity matter systems be asymptotically safe? Well, this is not a crazy idea of mine or some, let's say, young colleagues. This was proposed by Weinberg. But the caveat is that you have to go non-perturbative, which we all know that is very difficult. So Weinberg proposed this in this special issue that I think is precisely the same special issue where the Unruh-DeWitt detectors were introduced. And I think it's the last chapter of this special edition, this paper by Weinberg. And what Weinberg is proposing is precisely a generalized notion of renormalizability, which is not the perturbative renormalizability, but the existence of such a fixed point, or the finiteness of physical observables by the fact that you reach a fixed point. So in here, I'm going to write the asymptotic safety condition as the dimensionless counterpart of the essential couplings, and I'm introducing a bunch of jargon. They should reach an ultraviolet renormalization group fixed point. And at the fixed point, this coupling ceases to run, and you get what is called quantum scaling invariance, which is a little bit different from classical scaling invariance. So in this picture, if you think about regular space-time that we see, if you start to zoom in, then you're going to start seeing, well, this is just a cartoon, don't take it too seriously. You're going to see quantum fluctuations, and at some point, the couplings will just stop running, and then you're going to see essentially, if you continue to zoom in, you're going to see some sort of fractal structure. You're going to see some self-similarity. Space-time is just, will be just a fractal structure. Okay, so there are different strategies to address this problem. One is putting the theory in a lattice. You take quantum gravity, you take the path integral, you put Einstein-Hilbert action, you discretize that, you put in a lattice, and you do Monte Carlo simulations. So those brave people, they form what is known the causal dynamical triangulations community, and they try to find a suitable fixed point where you can take the continuum limit, namely where you can find a phase transition from this crazy discretized theory into a theory that we go to the infrared and recover the universe we see, for instance, the Sitter universe. So they do that, they do simulations, and they have evidence for the existence of such a phase. Other strategies is to do continuum quantum field theory techniques, namely functional renormalization group, Dyson-Schwinger equations, and you compute the beta functions non-perturbatively. And most of the progress in asymptotic safety was achieved by the use of the functional renormalization group. This brings several issues, but, well, this is how the field evolved. And while trying to search for this renormalization group fixed point, using whatever technique you want, is what is called the asymptotic safety program for quantum gravity. But mostly when people talk about asymptotic safety, they are referring to the FRG. Okay? But let me emphasize that FRG, or functional renormalization group, is just a tool. It's not the concept behind the approach. So just to make a very quick introduction to the functional renormalization group for those of you that are not familiar with, well, you start with your, and now to please Nami, I mean, I will do everything Euclidean, okay? So, so you start with an Euclidean path integral, you have an ultraviolet cutoff, and what you do, you introduce a mass-like term, so it's quadratic on the fields, then you have this function Rk, which has the purpose of suppressing all the modes that are below this scale k. So this means that effectively when you perform this integral, you are just integrating out the modes above the scale k. Okay? And this function Rk is arbitrary. Well, it can satisfy or should satisfy some consistency conditions, but at the moment I don't want to bother with these technicalities. So if you integrate out all the modes, so if you lower k down to 0, you get the standard effective action, which is the generating function of one particle irreducible diagrams, if you wish. And what happens is that you have this flow from the classical action, which is S, down to the effective action. And at intermediate steps, you have this gamma k, which is the effective action that is, let's say, a partially functional integration that you did. It turns out that this gamma k, which is also known as the effective average action, satisfies an exact flow equation, which is written here. And this flow equation is essentially, I mean, you can just start from the path integral and do some tricks and get to this flow equation. So this is an exact result. It's not an approximation. But you see that it has a very simple form. Okay? And essentially, I'm converting the problem of solving the path integral into the problem of solving this functional differential equation. So it's, I mean, it's hopeless. We're not going to solve that. However, here I gain some insights in order to make different approximations than just the perturbative one. Okay, so I don't want to spend too much time on the technical details, but what happens is that now if you take the scale derivative, the derivative with respect to k of gamma, you get derivative of the couplings that are in front of the operators, because gamma now is expanded on a basis that is typically infinite dimensions of all operators that are compatible with the symmetries of your theory. And these G bars, they are typically dimension-full coupling constants, and what I'm defining here is precisely what is called the beta functions. And the beta functions are the scale derivatives of the dimensionless counterparts of these couplings. And I'm measuring these dimension-full couplings in cutoff units. I'm introducing here G bar, for instance, is k to the d, where d is the mass, canonical mass dimension of the coupling G. So G bar, sorry, and G is the dimensionless version of it. So you take the scale derivative of gamma k, and now you just write down this expression for the beta function. You expand the scale derivatives on the same basis of gamma k, and you have the flow equation that I just showed to you. You expand the right-hand side of this flow equation on the same basis, and you can compare both sides, and you can read off the beta functions of these dimensionless couplings. And in order to do so, you don't need to resort to a perturbative expansion. That's the main point. But it does not mean that you cannot recover perturbation theory, because as I said, this is just a technique. So if you replace this gamma 2 on the right-hand side by the classical action, this is precisely the one-loop effective action that we learned in standard textbooks. Okay? Okay, so, well, I said that you have infinitely many operators, so you might be afraid that you have infinitely many couplings and therefore predictivity is lost. But if you have a fixed point, namely if you demand that the beta functions all vanish, then you see that if you now have a non-trivial fixed point, you can do perturbation theory around this non-trivial fixed point, and you take a point in the theory space, which is the space of all these dimensionless couplings, and you see that you get precisely that the scale derivatives of this distance between a point in theory space and a fixed point is given by this matrix, d beta I, d gj, times this distance. And if you diagonalize this matrix, d beta dg, this equation simplifies to this one, here, down here, which can be easily solved in this form. And you see that you have now a momentum, or let me call cutoff dependence related to a scaling exponent. And if this scaling exponent is negative, this means that when you take k to be large, you are not going to reach the fixed point unless this integration constant is 0. So this is what is known as an irrelevant direction. And if theta is positive, then zi, and you take k to infinity, then this will go to 0 immediately, namely the distance between the point that you are and the fixed point will just vanish, which means that ci is a free parameter, and we call this a relevant direction. So a predictive theory is a theory that features finitely many relevant directions. Okay? So asymptotic safety requires the existence of the renormalization group fixed point and also finitely many relevant directions. And I'm going to just go a little bit faster to get to the tests in the lab. So the technical side, well, there are already textbooks on this subject, which means that either the field is dead or we are trying to attract some more students to the game. And you can check that. And there is also a very nice paper written by John, which is a critique to the, well, I don't think it's a critique to the concept, but it's a critique to the way that we do the calculations. And I'm being, well, I'm trying to be honest and say that there are several caveats that I do not have time to explain in this game. Now let's move to quantum gravity. And unfortunately, I have to restrict, at least for the purpose of this talk, I will restrict to the Euclidean case, okay? So I will perform now this path integral in Euclidean signature. And in the morning we heard that in order to do physics we need a background structure. And yes, and we can use the background field method for that. We don't have to impose that the metric is classical from the beginning. You just split the metric as a classical background plus a fluctuation. This fluctuation h mu nu does not need to be small, okay? Well, then you have to do all the standard procedure in order to quantize this theory. You have to gauge fix, you have to introduce FADF Popov ghosts, and so on. And you get this very complicated regularized partition function where you have your classical action plus gauge fixing plus ghosts and regulators and sources, and so it's a complicated thing. And the effective average action now depends on the fields, the quantum fields, and the background fields. And the flow equation, remarkably, has the same structure as before. But deriving that is much more complicated than the simple one for the scalar case. And if you want to learn, you can check the master thesis of the guy sitting there, where he derives the flow equation in full glory for you. So you can check that. Also, since h mu nu does not need to be small, you can, if you start with a Riemannian metric, G bar, H mu nu can change signature of your metric G mu nu. Also, you can produce degenerate metrics and all sorts of pathologies that you're going to introduce in your path integral. So there is a different way of writing, of using this background field method, which is to write G mu nu as a background metric times the exponential of the fluctuation. And remarkably, of course, I mean, if you fix G bar to be a Riemannian metric, G will also have the same signature, and it was also proved that this parametrization covers the entire space of Riemannian metrics. So you're not really taking out Riemannian metrics. Okay, so now we have all the ingredients to make computations. You now comes the dirty part of the game. You have to make an ansatz for your effective average action. Namely, you have to truncate your effective average action. You compute the beta functions of the couplings, and you look for a suitable fixed point. This is what is done. And you have to enlarge the truncation in order to see whether this fixed point persists by some ordering principle that is not perturbation theory. And we want to investigate some possible onset or apparent onset of instability of the results. So the simplest truncation that you can think of is just to introduce the Einstein-Hilbert action, and you compute the flow of G, Newton, and cosmological constant, and search for a fixed point. And this was derived, and here is a nice flow diagram where you see that you have RG trajectories that flow to a fixed point. Well, you can say that it's a long and winding road towards the fixed point, but you get there by fixing G and lambda. And let me say that G and lambda in this case are both free parameters, so they are relevant directions. Now you can enlarge the truncations. John also pointed out you have to introduce all sorts of high derivative terms, but unlike what John presented, we don't introduce just R squared and R mu nu squared. We have to introduce all of them. And this is, of course, well, as we say, challenging. And, but of course, people have explored many different directions by enlarging the truncations, and the results are promising, which means that we do see some persistency of the existence of the fixed point. In particular, people have introduced, for instance, the Goroffi-Sagnotti term that is a cubic term in curvature, and this is an irrelevant direction, which means that this is not a new free parameter that you have to fix, as you would have to do in a perturbative scheme. Okay, very crazy people. Oh, this is on record, I should not say that. They started doing truncations with f of r forms with r to the 70 powers in order to see stability of the results. And you see here that after, I mean, n is big enough, you see some onset of stability of the fixed point. And what is the most striking result, in my opinion, for that, is that the number of parameters that you have to adjust, namely the number of relevant directions, is 3. So you introduce r to the 70, you have independent couplings for all of them, and just 3 of them are really independent. All the rest you can write in terms of them. Okay? Also, of course, you can say, well, I don't care. I can add r to the 75 and changes everything. Yeah, you're right. This can happen. But people are searching also for that, as I said, using different methods. So I think the main idea is to try to cross-fertilize these ideas. Towards phenomenology in my last minute. So, as I said, I would like to focus on the interplay between quantum gravity and particle physics and not talk much about cosmology and black holes. But there are some works in this direction that I will not mention at all. But again, the idea that was named as meta matters in this scenario says that, well, quantum matter, well, changes quantum space-time, which affects quantum matter and so on. This is the general idea. And the gravitational fixed point could be in danger if you add different types of matter. So, as I said, I mean, this was started by other people, but, well, this is my talk, so I'll talk about my work. And in this work, we have done some calculations where we started with this type of truncation. Now it's a function of r and r mu squared, and we introduce this matter action. So you see that this essentially just the kinetic term of each matter species, but I allow for any copies of scalar fields and copies of psi field, of fermion fields, and copies of gauge fields. Okay. Let me also say that one of the authors, Gustavo, is now a faculty member at Unesp in Guaratinguetá. So there is one person here in São Paulo now doing asymptotic safety as well. So this is, I just wanted to advertise that. So what happens is that you get this result. So if we introduce the number of degrees of freedom of the standard model, you do have a fixed point. If you add, for instance, 3 right-handed neutrinos to the game, which is phenomenologically plausible, you also have a renormalization group fixed point. But for instance, if the world was made of minimally supersymmetric standard model, you don't have the fixed point anymore. You lose the fixed point. This also happens for instance, SU5 grand unified theories. For SO10, we, at least in this truncation that we did the calculations, we found a fixed point. So matter content seems to matter for the existence of the fixed point. And for instance, if LHC just tells me that there is, that's the correct description of the universe comes from MSSM, then this will put this entire program in danger, at least in this calculation that we have done. So this is what I'm saying as testing this theory using the LHC. Okay, so just to make this very quick, now you can do the opposite. You can study the impact of quantum gravitational fluctuations to the running of matter couplings. And typically they appear in this form, linear on the matter coupling, and I'm parameterizing the gravitational contribution in this function f. And you see that now, because of the presence of this contribution, I can have, I can change the behavior of the beta function of the matter sector. Depending on the sign of f, you can push this coupling towards irrelevance or relevance. So some couplings that are relevant might become irrelevant, and therefore a prediction of the theory. So let me just go towards the result. So there is this famous result by Shaposhnikov and Wetterich, where they, using the, well, assuming the existence of the fixed point, they managed to predict the Higgs mass, and the value is outlined here, is 126 GeV. And I mean, there are several caveats in this calculation, but I have to say that this was done before the detection of the Higgs. Okay, so this is something that I think deserves some merit. And there is also, well, this is a much more recent work where there was a retrodiction of the value of the top mass, using again the postulating the existence of the fixed point and analyzing the consequences of that. We also try to start analyzing different mechanisms for neutrino masses that are compatible with asymptotic safety. And this was the first paper in this direction that we did, and we are now trying to analyze all these seesaw type 1, type 2, type whatever, and if they are compatible or not with the fixed point. A much more recent paper that is an asymptotically safe standard model plus quantum gravity, so they include everything, and they do the calculation, and what they find is that at least in their calculation, they find that the couplings of the standard model, all of them go to 0 after the Planck scale. So you have asymptotic freedom fully. Okay? I don't want to enter the details of this paper. It's a very long paper. It's not mine, so I'm just advertising the result. And also let me mention that there are these candidates, for instance, for axions for dark matter. And there is this recent work made by Gustavo and Rafael, who is also from Guaratinguetá, but now is living in Poland, which is axion-like particles, if they're compatible or not with the asymptotic safety scenario. And they find that it's not. So they say that there are no ALPS in the asymptotic safety landscape. Okay? And a review of what is going on in asymptotic safety and plus matter can be found in this work that was published in this handbook of quantum gravity that is definitely not, does not fit a hand. It's an insane book, okay? Okay, so there are final words. I don't have time, so I'll just stop and thank you for your attention for that.
Due to time constraints, guys, I have time just for one quick question, please.
So maybe even to foster the discussion during the break, it was basically known since the beginning when we were doing this that the Wetterich equation, the K parameter, is a mathematical parameter. And we cannot interpret the running in function of K as strictly physical running, only in some situation. And now there is a body of evidence and further study in the last year that have deepened this, that there is the mathematical parameter running and the physical running. So, and it was also clear that this affects, in particular, when you try to compute the gravitational correction to the matter sector.
Yes.
So I wanted to say, how much do you think, for example, that this will touch these kind of results like the one that you presented or the later one from the group of Astrid Ektorn and those of Jan Pawlowski?
Yeah, thanks for the question. Well, of course, you are absolutely correct. I mean, this is a mathematical parameter. This is not momentum, that you're not computing physical running. Of course, when you compute the physical running, the correction might be 0, I don't know. It might be opposite sign. But there is another issue that concerns me, which is how to define properly the couplings when you are in presence of gravity. Because typically, in a standard quantum field theory, you define by a local correlation function. And in the presence of gravity, those are not gauge invariant. So I'm afraid that even if you compute, let's say, in a more physical world, you still have to take into account these issues of gauge dependence and so on. So my answer to your question is I have no idea. Yes, but yeah. So, but then I think it's a different status of your question. Yeah.
So let's thank the speaker again, guys. And we'll stop for a short coffee break and we'll be back.